Okay, hello everyone. Welcome to the last lecture, lecture number 16, the last lecture of this course, of this series. And on previous lecture, we talked about this perturbation. I derived for you this perturbation theory for computing multi-time correlation functions for open systems with an application to this our fantasy of well, not fantasy, but of this uh, physical process of spreading thermalization, right? And it was a quite a technical, it was quite a technical topic there. But today we'll be talking about something more lighter, less technical, hopefully. And as you can see, the title, this is the chapter 8 from the script, the origin of external fields in quantum mechanics. Okay, so uh, you know, what do I mean by external fields here? Uh, so let me start with a maybe a simpler scenario. Let's before we talk about quantum mechanics, like let's go back to the good old classical mechanics, where this is in classical mechanics. Whenever you have a like a many body problem, right? The standard well-founded approach is to like you are trying to eliminate some of the some of the parties from your multi party system. You eliminate some of those parties and replace them with external fields, right? So the emblematic example would be, say, you have a star here. So we have a sun, right? Of course, you have to draw a face, and you have a planet orbiting around the sun, right? And they are, of course, interacting with each other through gravity. Let's denote small r the position of the planet, capital R position of the sun. Okay, and of course, if you want to solve this problem completely, right, you have to write down the dynamical equations for for r, for small r, and for big R, right? Second order derivatives, and you will have some force. You will have some forces, right? Let's say mass of a planet, mass of the star, some force depending on the position of the planet, but also position of the star, and perhaps even on time. And for the sun, the same thing, right? So you have coupled equations. Uh, the forces depend on position of both parties in general, right? And this is a two-body problem, which you can try to solve it exactly, but it's a well-known fact that with some change of clever tricks like a change of coordinate system, change of variables, right? You switch to the mm, mm, center mass plus the difference between the distance between the two bodies, right? And you do all those tricks, and in a in in the limit where mass of the sun is much greater than mass of the planet, right? It's like in a typical solar system. You can basically take those coupled dynamical equations, and you can eliminate from this the massive planet essentially, and treat it as if the planet here just moved in a external given gravity gravitational field, right? Gravitational force field generated by the star, right? So you eliminate, you approximate this by eliminating, right? You eliminate the position of the sun as a variable, and you basically represent the influence of this of the star onto the planet as an external field, right? And external force field. So in classical mechanics, this kind of trick, this kind of change of perspective, this kind of approximation is very natural, and the formalism of classical mechanics is very compatible with this kind of tricks, right? And in fact, you can argue that in in every system, many body system, where you have some coupled equations of motions, the particles are interacting, you can always rewrite it, by in a form where the equations of motion are decoupled completely, uh, and instead you rewrite everything as if all those particles moved independently of each other, but they are constrained by some very elaborate force fields, right? So it's like you can imagine that you have like two particles colliding, you have some scattering or something like that, but you can rewrite all the equations to reproduce the same movement, the same trajectories for both particles, but rather than this deflection generated by their mutual interaction, you can like construct very elaborated like tracks, force fields, right? Maybe time dependent force fields, velocity dependent force field. You can go you might be forced to do something very complicated, but like instead of interaction that repels particles and move and forces them to move on their paths, you can imagine that they just move on the tracks that they're moving on the very complicated tracks, right? So that the resultant motion is the same as if you just generated it through interactions, but on the level of equations, you just mimic it or simulate it with very maybe very complicated external forces, right? So this is like the idea of external fields, external force fields, external potentials in classical mechanics, right? It's very natural in its it's very natural in classical theories because the basically the formalism is very compatible with this kind of approach, right? This idea of mm, switching from coupled equations of motions to uh, uncoupled equations, but with added constraints in the forms of external fields. This is all like very, it's all doable in classical mechanics. But now, if you go to quantum mechanics, you know, silly tricks like that just don't work anymore because your equations of motion, you have Schrodinger equation, you have states, you have a product form of the Hilbert spaces when you have many body systems, right? There is no some very simplistic change of variables almost never works, or although sometimes it does work actually. So this scenario, like quantum scenario of a planet orbiting a sun, or more likely like electron orbiting nucleus. There are some, if the potentials are just right, sometimes you can do stuff like change of variables and do something similar that we did with that I try to explain what you can do with this solar system here. but it's more of an exception than the rule. Basically, like, while classical mechanics is very compatible with the idea of eliminating, you know, of transforming many body problem into single body problem with external fields is very like compatible with this approach. Quantum mechanics, the formalism of quantum mechanics is very resistant to that because you have to like it's intuitively speaking, it's not clear what you actually have to do. You like eliminate states, operators, observables, and replace them with functions to simulate this kind of external potentials. It's all very, uh, it's not clear how you can achieve all this stuff. Nevertheless, we know from experience that this kind of external field simulations, external field models actually work very well for quantum systems. You can go from something very simple like a Pauli Hamiltonian, very basic stuff. So imagine you have spin 1/2 a particle that's precessing in some external magnetic field. This is like very standard very standard model, right? So you have like spin operator, some coupling constant, and then external magnetic field, right? And the particle just evolves according to this Hamiltonian in this external field. And the more complex, more general models would be stuff that we talked about previously when we analyze stochastic maps for uh, for our uh, for our system, right? There, the external field was actually like modeled with even noisy, stochastic potentials and stuff like that. So that would be, on the other end of very complicated external field models, and this Pauli Hamiltonian would be something very simplistic. So it's a well-known fact that you can, even though it looks very unintuitive, seemingly, it's like it's not very clear how you can go from many body quantum problem to single body problem with external fields, how this procedure is supposed to work. But we know that it does work. There are cases when it does work, and it's a pretty obvious that mm, this external field simulations, they those external fields that we put into our Hamiltonians, like here, they almost certainly they come from some elimination of other quantum systems. Our system of interest is coupled to in reality, right? So on the fundamental level, we imagine that this is like this spin 1/2 particle is coupled to its environment, right? And we do some stuff, some approximations, or some tricks. Something is done so that we can eliminate the environment and replace its influence as this external field, external magnetic field. So in other words, if we are like interested in understanding uh, where those external fields come from in quantum mechanics, right? Uh, if we are certain that they come from their origin is as some kind of simulation or approximation to system interacting with its with some other system, let's call the other systems an environment, and the procedure most likely involves like eliminating the environment, right, and replacing with external field, where this seems like a job explaining all these procedures, seems like a job for open system theory, right? Because open system theory in the end is, you have system S of interest coupled to system E in the environment, and you eliminate right? You eliminate the environmental degrees of freedom from your problem, and so you could get an effective dynamics for the system S, and you incorporate in some way an influence from this interaction with eliminated environment, right? So this is what essentially what open system theory does, right? This is what it's supposed to do. This is what it's designed to do, right? And here we want to like use this insight from the open system theory to try to figure out what has to happen, what kind of environment is required, what kind of coupling is required, so that this elimination of environment uh, will produce a system S dynamics that looks like a coupling to an external classical field, external force field. Okay, so so we want to use our know-how from open system theory to basically figure out where do external fields comes from in quantum mechanics, because it seems kind of weird because it's not like classical mechanics, right? It's not the formalism is not very compatible with this kind of replacement, but maybe when we go through open system theory, our formalism, we will be able to like pinpoint what is going on actually, what's under the hood when you derive this kind of external field simulations or approximations to the real many body interactions, right? So this is the setup for our problem here, and and let's try to answer this question. Now, where do external fields come from? Uh, yeah, so let's move to the next section, 8.2. Surrogate surrogate field representation. All right, so imagine we have a many-body problem, the standard open system setup. So we have a system SE, right? System of interest, environment, standard stuff, right? And there is a Hamiltonian. So let's maybe I draw some cartoons. Maybe this will be helpful in some way. I don't know. So we have our system S. Boop. Some other color, maybe blue. Right, we have environment. And they are talking to each other, right? There's some interaction between them. And so let's write down the Hamiltonian. So we have system environment Hamiltonian, right? The standard form, Hamiltonian in S, Hamiltonian in E, right? And there is interaction. So we have coupling constants, an operator in S, an operator in E, in environment E. So this guy here is lambda S times E. And the idea behind this external field approximation, so what formally we would like to write down is like, so this is two-body problem, right? And we want to to do something like this, right? We want to eliminate one of the bodies, environment specifically. So we would like to move from this to some effective Hamiltonian in S only, okay? That's time dependent in general, and it has, the free Hamiltonian of the system is here, but the coupling, instead of coupling to the some environmental observable, you want to see something like we have an operator S here, but this operator E here is replaced by some function, a stochastic process in general, right? And stochastic process in general, because if you want to have something like this, so this is a constant, so a deterministic process, but deterministic processes, constant processes are just special cases for stochastic process. So we want to cover all options, right? So we will just get here some stochastic process E, right? So so we will, and this is a operator in system S only, right? We are getting rid of the environment completely, right? And replacing the influence, the coupling with the environment by coupling to this external stochastic noisy force field, okay, represented by stochastic process E. So because this is like what is happening here, we are like, we are positing here a replacement for coupling E, right? So this stochastic process E is a surrogate, right? Is a surrogate for the real environment E, right? So that's why we are calling this E a surrogate field. Surrogate field. Right? Because it is a surrogate for the real real quantum mechanical environment coupling operator, right? Right. So surrogate field E represented by a stochastic process. So this is what we would like to do, right? Mm, so when does when this kind of move yields a correct or accurate simulation of real dynamics, right? Because we are creating this, because this is a stochastic process here, so we should actually write it's time dependent, yeah, but it also functionally depends on so this is a Hamiltonian, stochastic Hamiltonian that functionally depends on the process E, and it's also, explicitly time dependent because of the stochastic process E. So we are trying to, we are interested in the dynamics of system S, right? But we know that system S is coupled to system E through this kind of quantum mechanical coupling, right? And what we want to do, we want to eliminate E from the picture, or in other words, we want to like simulate the dynamics in S uh, with this external field that mimics is a surrogate for the environment. So this kind of move, this kind of replacement uh, is successful, is valid, right? Provided that all the dynamical properties of system S uh, will be accurately simulated by this model, right? So we want a real system S dynamics generated by this Hamiltonian, by real coupling with real environment would be indistinguishable at least with some good within some good approximation from the dynamics generated by this surrogate Hamiltonian, right? That uses a stochastic process rather than real environment here, right? Replaces the influence from real environment with this effective surrogate field. So we have so how to quantify this how to quantify the accuracy of this kind of simulation? Well, the most like holistic way to approach this is to go back to reuse our by trajectory formalism for this purpose, right? You know, we learned that dynamical maps can be treated. Dynamical maps can be if you are interested only in single time correlation functions or expectation values of observables in S, right? So then it's enough to use dynamical maps, but we know that dynamical maps are essentially, it's just a certain superoperator averaged over by trajectory distribution, right? So this is what covers the state dynamics of system S, of open system S, right? But if you want to go to full, have total description of every possible dynamical property of system S, then you have to be able to, right, to calculate multi-time correlation functions. And we learned on the previous lecture that to do that, you have to be able to, to compute the by probability distribution for system S, conditioned by the presence of system E. Something that we called uh, by probability of open system S, right? And we called it on previous lecture a QS conditioned by E, right? And if to recall the definition, so we have a sequence of phi plus, sequence of phi minus, phi 0, phi 0. They are always the same. And the formula was trace over S, open brackets, and we had here product I from n to 1. We had here a projectors PS tau I, phi I plus bullet PS tau I, phi I minus. Okay, and we had propagators, time ordering over dynamical variable Z, Ti minus 1. So this is straight from the previous lecture. And we had Z, it's time dependent, but it also depends on environmental by trajectory, right? This is how we get influence from environment. And all this has to be averaged over environmental by trajectory distribution. And the last element is the tau 0, phi 0, right, initial condition. Right. So this is what we identified in previous lecture as a by probability for the system open to environment, where the coupling comes from the dynamical variable z, right? And you have the averaging over by trajectory of environment psi. Uh, and we showed previously that once you have those guys, right, you have everything, starting from expectation values, and going to any multi-time correlation functions, which in other words, every dynamical property of system S can be like quantified using those, can be derived from those by probability distributions, right? So this QSE is the, let's say, exact by probability, right? This is how it looks when you include the influence from the environment treated as a real life quantum mechanical system, right? As this. And now we want to do this surrogate field replacement, right? So in other words, we want to say that this thing can be accurately can be accurately simulated by a stochastic model. So we want to this to essentially want to do we want to replace the averaging over by trajectory distribution with a averaging over probability distribution for this surrogate field E here, right? So what we want to have here is that the real by probability distribution is with good approximation indistinguishable from a by probability distribution obtained from stochastic simulation. E U S U and all this thing, we have a stochastic average of all this stuff. This averaged superoperator acting on the initial condition. Right, so rather than coupling, just for completeness, maybe let me remind you what those things are. So ZU psi plus psi minus. So for this kind of simple coupling, so only one operator, this would reduce to eigenvalue psi plus at time u. You know what? Let me introduce a couple of. So E operator H E T E H E. So I'm just reminding you all the definitions that we used on previous lectures. So the interaction picture of the environmental coupling, right? wait one bit. So first, maybe let me introduce projection operator T phi and psi I H E T I T E, right? The transformation of bases. The coordinates and the interaction picture, right? If we have this, then the interaction picture of operator E would be simply sum over psi, eigenvalue psi P E T, and the coordinate corresponding to the transformation to eigenbasis of E. I will call this epsilon, this coordinate epsilon, psi. Okay, so when we have, so this defines for us the eigenvalues of operator E. And we remind ourselves about the definition of the projectors with space-time coordinates. And when we have this, then our z dynamical variable can be written as SU bullet minus bullet SU. And here we have E psi minus of T epsilon. Right, so this is a standard definition. Again, these guys here, projectors. So maybe first the coordinate tau I, space-time coordinate Ti, phi I, okay. And this guy here is a projection operator corresponding to projection operator in E. That is IHS Ti I basis transformation in S times phi I acting on the basis element. And you have the, so this is the ket part and the bra part. You can fill it in for yourself here. What else? What else? Okay, I think that's all the definitions made are made explicitly here. All right, so to summarize this, so we have a system environment, two party system, right, with S and E. They're coupled. The real dynamics is generated by this Hamiltonian with the coupling S and E written down here. We want to model this with this surrogate field where we eliminate environment and replace it with a dynamics in S only, where the influence from environment is mimicked, is simulated by this surrogate field, the stochastic process, ET. And the simulation, we can consider the simulation as a success. This surrogate field representation is a valid simulation when the all by probability distributions for open system S, which are defined in this way. So there is an explicit averaging over by trajectories of the environment, right? And we want, if those guys are more, are accurately approximated by probabilities generated for coupling uh, to the stochastic process E, we will consider our simulation to be valid, right? And the approximation to be accurate. So this would be the setup for this whole problem. And now the question is, okay, is it so now so this would be a criteria for this kind of external field surrogate field approximation to work. So now we have to analyze, okay, is it even possible to basically replace a quantum average over by trajectory distribution of environment? Can this be accurately replaced or mimicked by an average over some stochastic over some probability distribution for the stochastic process E? Okay, is it even possible? Can it happen that this average is indistinguishable from this average? Quantum average indistinguishable from stochastic average. So let me introduce some more formal elements to ease this kind of analysis. So one thing, because we will be writing this all the time. So let's do the standard thing and replace this super operator here, the intervention, with one symbol, pi, calligraphic font because it is a super operator. What else? What else? Okay, one more thing for the environment. Right, so let's assume also that the initial condition has a standard S0 times standard product form, standard for open system setup, product form. And let's also so this guy we can use our spectral decomposition to define all the elements for the initial state of environment. Sum over psi, eigenvalues rho E, and PE0 calligraphic rho. This is ugly. Let me fix this a bit. Oh, okay. Psi. Right, so coordinate transform to basis of the eigencats of rho 0 E and eigenvalues rho E. Okay, so this is all we need. So now one more thing I will do to simplify or enable our analysis. So let's consider, right? So here we have let's consider some arbitrary moment of dynamical variables. So we have a moment of dynamical variable z, so the real quantum dynamical variable z, which according to our definitions, so this would be a double integral. So we have here a product or the product of dynamical variables z. So let's write down them explicitly here. Eigenvalue of the coupling psi plus at ui coordinate epsilon. Right, one coordinate because there's only one coupling operator here. We have SU minus SI eigenvalue psi minus UI epsilon. Okay, so this is the dynamical variables, and now the averaging over the bitrajectory distribution for the environment. So we have this initial condition comes in as usual at time 0, coordinate rho e psi minus at the same time 0 and same coordinate rho square root, and the actual bi-probability distribution for environment. So this is the definition of average of moment. And now what I want to do is, so because there is only one coupling operator here, and this is the guy we want to actually replace with the surrogate field, right? So we can it's a little bit maybe it's unnecessary to, we are setting only this. I mean, this coordinate here is always the same. It's always the epsilon. Always the transformation to the eigenbasis of operator E, right? So you can maybe we can simplify this a bit and basically take this average here and change variables rather than averaging over psi of epsilon. Let's just average over, let's change variables to push forward from this bitrajectory distribution to a bitrajectory distribution that is associated with this concrete choice of observable E, this concrete choice of the transformation coordinate. So in other words, I want to change the variables of the integration to obtain the following form: E plus at UI SUI minus SUI E minus UI, close bracket, close bracket, E rho E plus E minus DE plus DE minus. So I changed the variables. So we went from this distribution, the original system E by trajectory distribution, and we changed the variables to, rather than integrating over psi plus psi minus, we're now integrating over the eigenvalues of E, basically, right? And we also absorbed the initial condition into the distribution QE. So after this change of variables, this new by probability distribution associated with observable E and the initialization QE, it's discrete restrictions discrete restrictions so discrete restriction means that I'm taking the values E plus I Ti. So I'm constraining the by trajectory E to specific values at specific points in time. These guys are then equal to trace over E. Product I n to 1 and sum psi E plus I. So the argument, right? This restriction, and here eigenvalue of operator E. So this eigenvalue P E T I epsilon psi. So this extra sum here, it appears because it's possible that operator E is degenerate. So some of the it is possible that eigenvalues are not number of unique eigenvalues is smaller than the dimension of the space, right? So there is the same value of same E corresponds to different eigenvectors, okay? Degeneracy. So this is basically summing over the degenerate subspaces. Mm, Rho E0. So if this is the case, then we can like simplify it a little bit even more. So let's just call this guy. So this is a project. If operator E is degenerate, this operator projects onto this degenerated eigenspace of the operator E. So let's just call this P E of Ti of E plus I. Okay, so this is a projector onto degenerate eigenspace of operator capital E associated with eigenvalue E I plus, right? And those guys, because there are combinations of actual fine-grained projectors, rank 1 projectors, you take they are orthogonal. They are orthogonal. So if you take a product of two of those guys, you get delta delta A prime PIE, and they also span identity. So you take all of them. So this is a complete set of orthogonal projectors, but if observable E is degenerate, they are not necessarily rank 1 projectors. So operator 1 in environment subspace. So this is a shorthand notation. And we can already immediately use it here. PE TI EI minus. Okay, so this is basically by probability, but without this degree of freedom when you can change change basis with each time step. Okay, because we are using only we are dealing only with only one observable, so we don't have to. We can just transform to this basis epsilon, right, and keep it fixed. So if we do that, we can just take this general by probability and just transform it, change the variables to transform it to this by probability that's associated only with this one choice of basis. Okay, and this is what you get in return. So once we do this change of variables. Now we can use it to transform the argument of this trace pi tz zu psi du. So this is the original average over the original by probability, this guy, right? Mm, and we we change, because I can expand it into a product, into a combination of moments, and in each moment I can do this change of variables like here. So I can uh, transform this guy into the following formula: pi time ordering z minus I lambda ti minus 1 ti z e index e up sub superscript, sorry. No, e plus e minus du. Let's close this guy and averaging over our by probability associated with observable e plus de minus, and this adjusted dynamical variable here. This is simply e plus at time u su. Right, so we went from dynamical. So what happened here? So we went from this zu to this. So this guy here, this is z e ui. E plus, E minus. Okay. So this is the form we will be working with from now on. Right. So now, all right. So now, to get our proper surrogate field simulation, surrogate field representation for our system environment, for our open system S, right? This quantum average, which we now transform to the averaging over bitrajectory distribution associated with observable E, we want it to behave indistinguishably from the average over some stochastic process, E, okay? Uh, so in other words, we want to figure out under what circumstances by probability distribution of bitrajectory and the distribution of bitrajectory behaves effectively as a probability distribution of unitrajectory, right? So that this is our this is what we are trying to see here, and so let us check in more detail how this kind of thing can be accomplished. So before we do that, let me make let's go for a short break. Let me refill my drink, and after a couple of minutes, we'll come back to our analysis. Okay, let's continue. All right, so our problem is, so we have this a quantum average over environmental by trajectory, and we want to figure out what has to happen, or even if it is possible, for this guy to basically reduce to a effective stochastic average. Yeah, right. And notice that if E plus is the same as E minus, right? This guy, if you look at this dynamical variable, and if E plus equals E minus, right? This guy turns into plus E minus equal E. Okay, so some function E. You will get EU SU minus SU EU, right? Which is nothing else but EU times commutator, right? Okay, simple enough. So bearing this in mind, du, and here is some right. So this is our this is our surrogate field representation validity criteria, right? We have this, so there is a bitrajectory E plus E minus, and we want to make it, we want to see what has to happen so that this bitrajectory average turns into unitrajectory average, where uh, essentially those bitrajectories are like this one and the same trajectory when they collapse into one trajectory, and then the dynamical variable uh, turns into this generator, which is characteristic for coupling to external, which can be simulated by coupling to external field, right? So the question is if this is even possible, right? Can bitrajectory distribution turn into unitrajectory probability distribution? Is it even possible, right? And what has to happen for this to be true? Okay, if we can figure out that thing, then we have our answer for the origin of external fields. Okay, to figure this out, we have to do some preliminary. I mean, to figure out how possible it is to get this, we have to do some preliminary checks. So I have a couple of assignments here that I will solve it here with you. So we have assignment 35, and it says show that the diagonal part of B probability distribution is non-negative. So what is diagonal part? Diagonal part, where diagonal part, let's call it P E rho E Tn 0 E n. By definition is just you take by probability associated with E, same timings of 0, and you just set both components of this by sequence to be equal. So rather than feeding it with E plus and E minus, put the same the same sequences in both arguments. Right? So this is a diagonal part. Of diagonal part would be when there are some of the arguments are some pluses are different from minuses, and our task is here to show that it's that this thing is non-negative. Okay. Yeah, so let us do it. Let us do the calculation here. Maybe let me switch to green. Solution. It's actually not very difficult. So let me introduce certain operator. So let me take Q, small q operator, E n. Okay, let me define it as product n I from n to 1 p e t i e I. So you have product here, density matrix, and we have the product going other way, backwards in time. TIEI. Okay, so this is a definition of this operator Q, this matrix Q, and of course it's such that Q E row E, the diagonal part of by probability equals trace of Q. Right? So small q is the argument of a trace inside that defines full by probability. Okay. So having this in mind, okay, let us recall that operator A is non-negative. Okay, operator is non-negative when A can be written as this kind of product of some operator O, dagger times operator O. So this O can be viewed as a square root of A. Okay. If you can show that operator can be written like this, then you are dealing with positive semi-definite matrix and also Hermitian matrix, because all positive semi-definite operators are also Hermitian. Yeah, because positive semi-definite means that all eigenvalues of operator are non-negative numbers, and the Hermitian operator is when all eigenvalues are real numbers. So non-negative numbers are real, are also real, right? So positive semi-definite operators are Hermitian, also Hermitian. So this is if you have some operator A and you can show that you can decompose it into this kind of product, you immediately know that it's positive semi-definite. So in particular, therefore row E0 can be written in this way because row has to be positive semi-definite, right? So its square root is well defined, and having that so we take our operator Q and we want to decompose Q in this square root form, modulus form, which is simple enough. So we have a product of projectors PE, TI, EI, and we have density matrix, which I will write as this decomposition because it's positive, and we have the reverse product of projectors, right? So there are same projectors on left and right side, right? But they are just reverse orders. So in other words, this guy here, equals the guy on the left, on the right, sorry. 1 to n PTI EI, but daggered, right? Because what dagger would do would reverse the order of all the operators in product and apply dagger to each operator in the product. But projectors are Hermitian, so dagger does nothing. So daggering the left sequence produces you the right sequence. And so knowing that, we can write this guy here as a, let's open the a bracket, and we can write it as O product I 1 to N PE TIEI dagger, open bracket, take this O and take the product 1 to N right? So you can call this guy O Q dagger, and then this guy is just O Q. Okay. In other words, we decompose Q into this form, thus showing it's real. It's positive, semi-definite. Okay. So all its eigenvalues are positive, are non-negative, and so we get from this that P E, the diagonal part of by probability, equals trace of Q. Yeah, right. Trace of an operator is sum of its eigenvalues. So let's call eigenvalue eigenval of Q. All right. Because it's positive semi-definite, each of those guys are positive and non-negative. So this whole thing is non-negative, which is what we were supposed to show. So the diagonal part of by probability is a non-negative function. Okay, that's one. So this is the first thing. So then we have another assignment, another thing to show. Assignment 36. Show that the diagonal part of B probability is normalized. That is, we want to show that if you take sum over whole sequence of E's for Q E row E, it's not necessary. Whatever sequence of timings, En equals what? Solution. This is pretty easy to show. So we can, where do I have it? Sorry. Okay. All right, so we can use here our operator Q we defined here. We'll be using it a lot in upcoming our upcoming analysis. So let's take so here we have to show that sum over all E's. I mean, whole sequence of arguments is gives us 1. But let's start with a sum over just the last one. So this is the last of the sequence, last argument from the sequence, and we take our Q row Tn 0 En, which by now we know it is a So we are summing over the last, and we are summing trace E of operator Q. Okay, we introduced previously. Yeah. All right. But now we know trace, so we can enter the sum under the trace. And operator Q is basically right. You take the density matrix in the center and you start sandwiching it with projection operators from both sides. So I can write this as P. You know what? Let's let's keep some outside for a second. Trace E. So let's take the last guy, the last sandwich, En, and then we can QEn minus 1, PE Tn En. Right? Since Q is this sandwich, so I just peeled off the last the pieces of bread, the last piece of bread on the left and the last piece of bread on the right. And what you are getting is a smaller sandwich, but it's still the same form as Q. Just the sequence ends on Tn minus 1 rather than Tn. So this is what are written here. Now I can use a cyclic property of trace to move this guy to the left, right? And then I have then I multiply this projector with this projector, but they are the same projector, so they just orthogonality of projectors. So they just compact into a single projector. Or in other words, PE Tn En times PE Tn En equals PE Tn En. Okay, so two projectors, move one using the cyclic property of trace to here, multiply with the other projector, and they will then compact into a single projector. And now we enter with the sum. Trace E, sum over En, PE Tn En. This is the only thing that this compacted projector, the last projector, is the only thing that depends on the last argument. And of course, complete set of orthogonal projectors. This is just identity. So you get trace of Q Tn minus 1, En minus 1. Or simply Q E rho 0, Tn minus 1, 0, En minus 1, En minus 1. So summing over the last argument in the sequence shortens the by probability by 1. All right. So now using this relation, we come in and we do the sum over the last one, then we do the sum over the last one of this sequence, so En minus 1 argument, and so on, so on. So if you iterate it over all the time steps, E1 rho Tn. if we iterate over all the guys, we will eventually get to the E1 trace over PE T1 E1 rho 0 E. We will shorten it to the very last projector, cyclic property, move it here, compact them, sum over E, and we will eventually get to the trace of the initial density matrix in the middle, and this is 1. Okay. In other words, we just showed that we've proven this, okay, that it's normalized. The diagonal part is also normalized. So it is now we know, we just demonstrated that. Let me find my place. Okay, I'm here. So we just demonstrated that the diagonal part of biprobability is normalized and it's non-negative. In other words, this P E rho E Tn of En equal to diagonal part this can serve as a probability distribution distribution for a stochastic, not process, not yet, but a stochastic vector. Right? Because this is a probability distribution, a multivariate probability distributions for all those for En minus 1, and so on and so forth. So because each of those functions for each sequence of timings we just showed, is normalized and non-negative. So for each of those sequences, it can serve as a probability distribution for this specific sequence of times, okay? So it is a multivariate probability distribution. It's not yet a probability, like a joint probability distribution for a sampling of a trajectory of stochastic process, because there is one more condition that those functions P would have to satisfy. It's not just that being a probability distribution is not enough. You need another thing, which we introduced like back in the one of the first lectures when we talk about stochastic processes. For this family of multi-time probability distributions to be actually representing a sampling of stochastic process, they also have to satisfy this consistency condition, right? And diagonal parts of biprobabilities in general don't satisfy this consistency condition, which brings us to the final assignment 37. Show that in general, the diagonal part of B probability of B prob violate Kolmogorov consistency condition. So Kolmogorov consistency condition means that you have family of multi-time probability distributions like we have here, show that they are probability distributions, right? And you consistency conditions to be satisfied, you take any one of them and you pick one of the timings and you marginalize over this timing, let's say EJ, and for the consistency condition to hold, you would have to recover a probability, multi-time probability from this family you are investigating, where the marginalized timing is just knocked out. Just get the shorter distribution for shorter sequence. Right? And we want to, so if this equality holds, we would say that the family of multi-time probability distributions satisfy Kolmogorov consistency condition, which then, as I explained to you like many weeks ago, this means that those probability distribution, I mean, it immediately implies that those probability distributions are simply a discrete time restrictions of this master unitrajectory distribution. In other words, if the consistency holds, then those probabilities represent a sampling of a stochastic process. Okay? If they don't, and this is what we're supposed to show, that this is not, in general, not satisfied for diagonal parser by probabilities. If they don't, then those are just some collection of multi-time probability distributions, but those sequences cannot be treated as a trajectories of stochastic process. They are just vector stochastic variables. Okay. So yeah, so let's just show that this is the case. That quantum mechanical distributions are not like classical distributions, essentially, which is, this is how it's supposed to be. Okay, so solution. So we want to show that diagonal parts are not consistent, okay? But first, I will show that by probabilities, so full by probabilities are consistent in a sense, are biconsistent. So I will show B probes are B consistent. So what I mean by that, so let me take a by probability distribution here, sequence of timings. If we take, not, just by probability, not diagonal part, of diagonal part also. And now we marginalize, we pick one of the timings and we marginalize, but we sum over both arguments, plus and minus argument independently. And when you do that, let's see what happens. So, by probability, by its definition, it is we have our projectors here, a sequence of projectors, and along this product, you have a projector at timing tj that depends on ej plus. So the ej plus we are summing over. So let's just pull the sum in, ej plus, tj, ej plus. Okay, and we go along. The rest is unaltered. E1 plus. The density matrix in the middle. And we have the other side, right? We start from T1, T1 minus, product, and we eventually get to the EJ minus, which we are summing over. TJ, EJ minus, and so on. Close the brackets. Of course, these guys, complete set of orthogonal projectors. This is identity, and this is identity also. So what you get here is trace Tn plus. And if the projector at the position Tj, the jth position, it turns into identity, it just disappears, right? So you have Tj plus 1, Ej plus 1 plus, and Tj minus 1, Ej minus 1 plus, right? The Tj guy is missing. And you have the same kind of thing on the other side. Tj minus 1, Ej minus 1 minus, Pe Tj plus 1, Ej plus 1 minus, and so on, close the brackets. But this thing is simply QE rho E, Tn, Tj knocked out, T1, 0, En plus, Ej plus knocked out, En minus, Ej minus knocked out, E1 minus, right? So this is like it's like consistency, like Kolmogorov consistency, but for biprobabilities. So biconsistency. Okay, and this is actually this is important feature for like Kolmogorov consistency condition. If this would be satisfied, this would lead you to the stochastic process, right? So the unitrajectory distribution, and so is biconsistency. This is what's necessary to get a bitrajectory distribution. It's not sufficient. There is one more conditions have to satisfy on top of biconsistency, but it is necessary at least. So now I will use this to show that the diagonal part alone is inconsistent. Okay, because this biconsistency, it works for every sequence of timings and every sequence of arguments, E plus and E minus, except for the one we are summing over, because we are summing over everything. So in particular, we can take this this equality and set all the guys, all the arguments to be equal to each other. Essentially to take diagonal part of this guy here, right? So we take for I not equal j, we take ei plus equal ei minus equal ei. Okay, we set them to be equal. We set them to be equal, and I will take the why do you want to do that? Yeah, okay. And let's take that. So I will start by from the right side. So if I take them to be equal, by probability on the right side, the reduced, the shortened by probability just turns into, P, into the diagonal part. So right side, you get E rho E, Tn, Tj, this is knocked out, T1, 0, En, Ej knocked out, E1. So this is the right-hand side. On the left-hand side, we have so we have this sum here, okay? So let me do something about the sum. So let me split the sum into sum over Ej plus the sum where Ej plus is unequal Ej minus, right? So here you have sum over independent sums over plus and minus. So I can take a part of the sum where the plus and minus are equal, so the diagonal part of the sum, this is it. And then what I'm left with is a sum where they are unequal. So this is what this other term represents. And I take Q rho E Tn 0, right? And we have everything is all the arguments are the same except for jth, the argument at the position j, because we are summing over them, right? And then if I take the first part, I'm summing over I'm setting those last off diagonal terms to be, I bring them to diagonal. So I get sum over Ej Pe rho E Tn 0 En. Okay. So this would be like so this is the right-hand side of this equation we have it here. So this is one side of the Kolmogorov consistency. Boom. And this is the other side, right? And if we could end here, we would get a consistency condition satisfied, but we cannot get there because there is one more term. We just use the diagonal part and we still have off diagonal part. You have plus, you have a correction, a quantum correction by trajectory correction. J plus. And in general, this guy here is just non-zero, all right? So there is a non-zero correction coming in, which means that, we violate the consistency condition, which we were supposed to show here. All right, we are almost there. We have all the pieces in place. So now we know that the diagonal part of by probability distribution P are probability distributions because they are normalized and non-negative, but they are inconsistent in general because of the off diagonal parts, right? So this is what uh, holds back this diagonal part from being a distribution for a stochastic process, right? This is what is holding us back. Therefore, if we let's go back here. If we want to make a by trajectory distribution to be indistinguishable from averaging over stochastic process, right? The thing we have to take care of, we have to get rid of this bothersome guy, right? If it happens, so if the system E, the environment is such that the off diagonal parts of its bi-probabilities are just disappear or with good approximation can be neglected, then we will be left with only with the diagonal parts, which are then automatically consistent probability distribution that actually define a stochastic process, a surrogate field, right? So in other words, for the surrogate surrogate field representation is valid when the by probability distribution by trajectory distribution is such that everything except all the cases when the components of by trajectory are not overlapping are zero, have zero measure. Or in other words, that only the diagonal parts are non-zero. So we can write it as, you can put here deltas. Let's write it like that. So component plus must be equal to some one trajectory E. Component, so one function E. Same for minus, equal to the same function. Right, and then we have only the diagonal part contributes, and we can rename this diagonal part as P. Let's rename it as PE rho E of E. Okay. Then if you take a discrete restriction, it will be only the diagonal parts will survive. En plus and minus Q E rho E En En. And those guys are, of course, our diagonal parts P. P rho. Which we can treat as a discrete time restriction of this P here, of this master unit trajectory distribution. And we know that this guy is positive, is not non-negative, normalized, so this is a proper probability distribution. And on top of that, it's also consistent, because if by probability is proportional to deltas, then this term automatically vanishes and you get you satisfy the consistency condition, right? So this is all, in other words, you get this surrogate field representation when your by trajectory distribution actually behaves as a uni trajectory distribution because of the components of by trajectory are collapsed for some reason into a single uni trajectory, right? And if this collapse uh, takes place, then by the virtue of the properties of by probabilities and by trajectory distributions, you automatically generate a probability distribution for stochastic process E, with trajectories represented by this collapsed by trajectory. Okay. So if this is all, if all this works, so if this is satisfied, if our environment has properties that lead to this kind of bi-trajectory collapse, then we get our criterion validated. So if I write down again, E time ordering minus Z Ti minus 1I ZUE plus plus minus. Oh, sorry. Sorry, this is. Let me save some time. No. I will write it down. So we get our, if this all works, so if we go back to our criteria, minus I lambda, Ti minus 1 Ti, and we have here Z E U E plus E minus, right? And now we substitute for Q this form, okay? So with good approximation, you get, so the double integral just turns into single integral because of the deltas. And E plus turns into E minus. They are the same, right? So you get here a diagonal part of dynamical variable, which, as we discussed previously, this is simply equal to E, U, and commutator generator in the form of commutator, close brackets, P, E, rho E, right, the diagonal part. And this is a probability distribution for a stochastic process E with trajectories. So this is a stochastic process E with trajectories in the form of this collapse components of bitrajectory. So this guy is simply equal to stochastic average. Which is exactly what we wanted to achieve. So we have this and stochastic average. So this is the secret sauce. This is the secret ingredient of this whole stuff. For external fields to appear in quantum mechanics, you have to have a coupled coupled system, you have to focus on one of the systems. So you turn into a open system scenario here. Have your system S coupled environment, and then the by trajectory distribution representing the environment. Well, the by trajectory distribution associated with the specific observable system S is coupled to, okay, it has to be such that it collapses into uni-trajectory distribution, okay? And if this happens, if this is how environment works, if this is the interplay between the dynamics in the environment, between Hamiltonian and this uh, initial density matrix and the coupling E and this observable E, if the relations between them are such that this collapse occurs, this B trajectory goes into unit trajectory, then from the point of view of any dynamics in system S, it appears as if system environment did not exist, but rather that the system S sees an external external noise, external field that's possibly noisy, right? It can be represented with a stochastic process, this stochastic process E, with probability distribution determined by the collapse by trajectory distribution. So if this is all, if the environment cooperates with us in this way, then we get our external field. The environment can be represented by this surrogate field. The observable of the environment can be represented by this surrogate field. And now the question is whether, so this would be a theory. So this is a theoretical prediction, okay? And now the question is, can you actually see this kind of collapse in real life? Are there systems that for which this thing actually occurs? And if they do exist, will they actually reproduce for us the known external field Hamiltonians, external field models like this, let's say this Pauli Hamiltonian here? And the answer is, well, obviously yes. Obviously, you can show examples, but they are kind of involved because, as it turns out, there are many scenarios, there are many types, very, very different mechanisms behind this kind of effect. And here, I won't go over them here, just because it would just take too much time, and it's kind of technical. But you can check out the notes, okay, the paper. Here, I go over in detail over three types of environments for which you get this surrogate field representation. Uh, and they are pretty interesting. I mean, some of them are less interesting than others, but you can you go over this, it's described in detail, and you can see that the mechanisms are very varied. Okay, it's not like only one thing. You don't have to have this fine tuning to get this kind of effect. Those examples showcases that all the usual suspects are here. So you have for example, we have here an example where you get this surrogate field representation when the environment is big. So this is like the action representing the environment is large in comparison to Planck constant. You also have an example with the environment that undergoes decoherence, certain types of decoherence, where you can get this. And there is one more example, which is not listed here, but it's someone else showed it there's a paper you can find describing it where it's an environment that's chaotic. Okay, chaotic. So you have big, massive environments, or approaching a classical limit. You have a special types of decoherence, or your system is chaotic, or any combination of those different reasons. All of them very different mechanisms. The math is very different. The theory is very different. But they all, in the end, give you this surrogate field approximation, where your bi-probability distribution is such that bi-trajectory collapses into uni-trajectory. And all those different scenarios will, in one way or another, reproduce all the examples of external fields, Hamiltonians of external fields that you can encounter uh, in textbooks and stuff like that. And also, answers couple of other questions, where the noisy fields comes from. So, where the stochastic process, the surrogate field is represented by actual stochastic process, not like degenerate stochastic process that's actually deterministic process. And, how the averaging comes in and stuff like that. So the theory is fairly simple when you break it down to the constituent parts, right? So you have to have a scenario of open system where the environment, the bitrajectory distribution of environments is such that bitrajectory actually collapses into unitrajectory. The physical realizations are numerous and varied, okay, and all the usual suspects are there. And and it answers a lot of questions, about this origin stuff. So that's the so if you want to see the examples, analyze the analysis of those examples, check out the notes. Okay, I'm here. So the one last thing I want to so this is like a technical aspect of the origin of external fields, of the surrogate field representation. But there are also there's one more aspect that's maybe a little bit more philosophical, but it's also very interesting, I think. And this time we will have we still have to use a little bit. We have to go over a little bit of math, but hopefully it will be much simpler than before. So again, this is the mechanism. So bitrajectory, if environment such that bitrajectory collapses into unitrajectory, you have your surrogate field representation, external field representation. But there is one more interesting aspect to this. Let me entitle this next section, maybe purple. 8.4. So 8.3 are the examples. You can check out them in the notes in the paper. Objectivity of surrogate field. Okay, so this sounds mysterious, right? But let me explain. So one thing to note, I mean, there will be a couple of things to note, but the criteria for surrogate field to work, surrogate field representation to work is a criteria about biprobability distribution for the environment. by probability distribution associated with an observable of belonging to the environment, right? And you know, I believe I already mentioned that, but this by probability, right? It's a yeah. If we just look at the at its definition, formula that defines it. Where was it? Here it is, right? So this thing here, even though the surrogate field representation is a so you have your system S, right? It's coupled to environment, and you talk about this external field, surrogate field representations, how this environment is seen from the point of view of the system, right? Because we want to simulate the dynamics of the system S with this with this by eliminating environment, the real quantum environment, and replacing it with this effective surrogate field, right? So the validity of surrogate field representation uh, is contingent on I mean, it is valid when it looks okay from the point of view of system S, right? Okay, this because it's supposed to simulate the dynamics of system S, right? But whether this surrogate field actually exists, this representation can be constructed, right? It all depends on the on by probability of observable belonging to the environment, right? And this by probability is defined only by the dynamics inside the environment, right? This Q is completely independent of the system as the surrogate field is supposed to couple to. Okay, so uh, and this is understandable because the by probability distributions, right? That they are in this by trajectory formalism, by probability distribution, it represents the system, a specific system, a system environment system in this case, right? So whether the surrogate field representation is valid for simulating dynamics in S, it all depends on the properties of by probability distribution characterizing environment, and whether it has this effect of collapsing by probability by trajectory into unitrajectory. It can depend only on the properties of the environment itself. None of this, whether this you have this collapse, it all depends on those operators living in the environment subspace. Nothing about system S has any influence over this surrogate field, this collapsing by trajectory collapsing to unitrajectory effect. It doesn't matter what system S is. It doesn't matter in what way the system S couples to environment. The only thing that matters is what happens in the environment. Okay, so uh, in other words, if your by environmental by probability uh, behaves like this, so the observable E has a valid surrogate field representation, it will be valid for any system S that is coupled to it, right? So if I take my original system S that we started our story with, right, and I replace this system S, I replace it with some system S prime, some completely different system, but I still couple it to environment by this form of coupling. So I'm still coupling to observable E. The system S prime will experience the same surrogate field as the original system S, okay? Which reflects the fact that this validity of surrogate field representation is just the property of the environment, right? So in this sense, if you make this like a philosophical statement that you treat those systems as you couple to this observable E as like observers, non-classical in general observers, quantum observers of this observable E. So as system system S is a quantum observer of observable E. Okay, right? So our system S that is coupled to observable E, if let's think of them as like a quantum observers of this observable E, all right? And now because the surrogate field representation depends only on environment, so it if it works for every system S in the same way. So all those quantum observers, they will agree that they see the same thing when they uh, uh, when they experience this coupling to the observable E. So in this sense, the surrogate field, if it works, it is intersubjective subjective among all quantum observers. Subjective, you know what subjective means. Subjective means that, one observer has certain experience about the thing it observes. Intersubjective, this is intersubjectivity means that when you gather some collection of observers, let's say quantum observers, and now you ask them ask them to compare what they experience about the observed thing, they will all agree. So their subjective experiences are equivalent among their peers. Okay, so it's like so you can say that objectivity. Objectivity would be like when is achieved when all the possible observers agree on their subjective experiences. So you have like intersubjectivity extended to all possible observers would be something that you could upgrade to objectivity, right? So uh, at this stage, we can say that surrogate field, this uh, stochastic process E that represents this observable E, because it's whether it's valid or not, it's only dependent on the proper dynamical properties of the environment. It makes it intersubjective among all quantum observers. That is, all systems S that can couple to observable E. Uh, okay, but this is only a subset of observers, let's say. To make this surrogate field really objective, to upgrade it on higher level than just this intersubjectivity, you would also have to demonstrate that it's actually also non-quantum or classical observers also experience this observable E as as this surrogate field, as this stochastic process. In other words, now what would happen if we actually try to measure the observable E as classical observers? We would try to measure the observable E, this operator E, directly, right? So we know that systems S coupled to E experience this surrogate field. You can imagine that they see it as those trajectories, but we also know that you also have to average over all those trajectories, right? So if you imagine maybe those trajectories are just some artifact of this description, right? Because you know there is no way to couple any system S to any kind of system S through any kind of coupling to this observable E in such a way that you can like isolate only one trajectory and skip this averaging here. So maybe those trajectories are like fake, effective entities. Uh, so what will happen then if I actually try to measure as a classical observer? I will try to measure this E. Will it appear to me as as a trajectories, or will there be some kind of averaging, or what will happen actually? Can I say that I will experience as a classical observer the same thing as those quantum observers experience when the surrogate field representation is valid? So in other words, what I want to see here, uh, I want to demonstrate to you that actually when you do a classical measurement, I mean, the classical observer will measure observable E. It will also agree with quantum observer that you see the same surrogate field as they do. Okay, and uh, and this is all. It all hinges on the fact that the bi-trajectory distribution that turns into probability distribution for unit trajectory, this is all independent of anything else around it, right? And all observers, quantum observers, classical observers, they actually derive what they see from this by probability here. So then if this by probability is acts or behaves as a classical stochastic process distribution, then all the observers, quantum and classical, will essentially experience the same thing. They all will see the same external noisy force field. Okay, so let me show you that as the last thing of this whole course. Let me go over that. Mm, so so the idea is to basically forget about open systems for now. So we 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 have this pair, system environment pair, and let's now forget about S completely. We just have E only, all right? And more than that, we want to focus on the observable capital E specifically, and we as a classical observers want to do measurement of this E, but we actually want to like try to probe its uh, trajectories, its unit trajectories. So we want to observe this observable E uh, over time. So we want to do a sequential measurement of this observable. So how do you do that? Well, there is a procedure for doing that. So measurements, maybe direct measurements of observable capital E. Okay, the one which we imagine has the valid surrogate field representation. So uh, so we'll go in steps here, all right? So I mean, okay. So imagine that we are doing measurements of this observable in this idealized scenario where your measurement you deploy some kind of measuring device as in standard formulation for quantum mechanics. You do your measurement, you get one of the eigenvalues of this observable E as your result, right? but your measurements are, let's assume, are not destructive, so that you can, once you are done with your measurement, the system evolves freely afterwards with this effects of you doing the measurement being that the state of your measured system has been modified by what you saw according to the collapse rule. Okay, so we want to chain the measurement, the Born rule for measuring observables together with the collapse rule to chain them together into a sequential measurement of observable E. So that's the standard theory behind it, and in practice, let's move step by step here. Okay, so we begin the first step. Initial initialize system E in state row 0E, right? So this is the same initial state as before. Okay, initialize system in state E. Allow it to evolve freely for time t1 greater than 0, and then do the measurement. So according to the Born rule, the probability of getting any specific result E1, so probability that we get result E1 given that the state of the system was row E T1, so initial row E evolved for time T1. So evolve freely. This means that row 0 E evolves to row TE, T1 E, equal to E minus I T1 Hamiltonian, free Hamiltonian of the system, I T1 HE. Okay, so we initialize it in the state row 0, allow it to evolve according to its Hamiltonian HE for time T1, and then we do the measurement, projective measurement. So according to Born rule, the probability of getting a specific result E1, so one of the eigenvalues of observable E, given what was the state of the system at the moment of measurement. So this equals to Born rule. Born rule tells us how to calculate it. So this is trace over E. You take a projection operator times 0, projection onto eigenspace corresponding to eigenvalue E1, and you put here the state. Row 0 E, E81 HE. Right, so this is a standard Born rule from standard quantum mechanics for Born rule. But now you use cyclic property to switch to Heisenberg picture. So you make it trace PE T1, also a standard move, right? But projection operator, you can the square of projection operators is projection operator again, but it also works other way, right? So I can take a projection operator and turn it into a square, and then use cyclic property to move the other one wherever I wish. So this guy actually equals to trace PE T1, E1, row 0 E, PE T1, E1. But this guy here is just Q row E T1, 0, E1, E1. This is a single time by probability, a diagonal part of a single time probability to be more precise. So this is P E row E T1, 0, E1. So you see the by probability pops in, right? Okay, so that's the so this is the first step. We measure, we initialize, allow it to evolve for T1, do the measurement, and the probability of getting a result E1 according to Born rule is just given by single time by probability, the diagonal part of single time probability. And now we want to continue. So now it comes in to continue on towards the next measurement, where we have to now deploy the collapse rule. So collapse rule. The collapse rule tells us that once the measurement is concluded, we have to do this assignment to the state of the system post-measurement, right? So collapse rule tells us that row ET1, so this was the state at the moment of measurement, it changes to given result E1, given that we obtained result E1, it changes to row E T conditioned on T1. So this will be a density matrix assigned to the system at time t that's later than T1, given that at T1 we measured result E1. Okay, this is the notation. And according to collapse rule, this guy has the following form. So this is the evolution post-measurement, right? So we have a unitary evolution operator. Let me try to fit it in. Maybe let me construct it differently. So we have a the density matrix at time t1, at time of measurement. Okay. Then the collapse rule tells us because there was a measurement at time t1 and we measured result E1, okay? So you have to collapse this density matrix, which is realized mathematically by sandwiching it with projection operators. E1, okay? And once you do the collapse, you can continue on evolving freely from that point in time, which this is where the Hamiltonian comes in. Okay, so we evolve it like any other density matrix. T minus T1, HE. But this thing, it's this operator here, after you do the sandwiching with projectors, it's not properly normalized. Its trace is not 1. So the collapse rule tells us that, okay, so you have to now renormalize it to make it all good. And the normalization is just probability of getting the measurement. Okay, so this is the collapse rule in action after one measurement. And this thing, with some very simple algebra, we can replace this probability we know from previous step that this is the diagonal part of by probability. And this guy here, this density matrix is row 0 E I H E T1 E minus I T1 H E, right? So you can use the evolution operators from here and here to switch to Heisenberg picture for projectors. And once you do that, you can recognize that you're getting in the numerator ITH. So this is the evolution post measurement, and the density matrix and projectors we can represent them by this operator Q we introduced previously when we were solving our assignments. And the guy here, let's just use our diagonal part, which also, just as a reminder, this is a trace of Q T1 E1, right? So this is this operator Q. So this is a collapse rule after first measurement. So now we want to do another measurement and time another, not her measurement at T2 greater than T1. So the probability of getting result E2 is given again by Born rule, but with the Born rule under the condition that you put here the collapsed state as your condition. So prob of getting E2 given that your state is T2 was collapsed at time T1 and now it's time T2. And you do the math. This is of course trace P0 E2 and just put here the density matrix 2 conditioned by 1 E1. You do the math and you get that it's actually equal to P E row E T2 T1 0 E2 E1, and the normalization comes from here. P row E T1 0 E1. Okay, and how does it happen? Well, collapse state is basically Q, evolved Q for a while. So if I substitute this guy here, you get Q, evolve it. You put here another projection, which you can split into a square, move it here, use the evolution operators to switch to Heisenberg picture, and you restore Q T2 T1 divided by the normalization, which is here. And the trace of Q T2 T1 is just the diagonal part of by probability. So this is how you get here, right? So this is a probability of obtaining E2 given the collapse state from the previous measurement. Uh, of course, you do the collapse again. E1 changes into T given two previous measurements, two previous results. And this guy, if you just iterate the collapse rule here, you won't be surprised that you will find that it's EI TH EQ T2 E2 EITHE divided by trace of Q T2 E2. So this is a collapse. So, again, the same thing as here. And now, so this is a probability of the conditional probability for getting E2 given what happened before. So the probability that you measure a sequence E2, E1 at times T2 let me write it like this. So the probability of measuring a sequence at times T2, T1, given the initial condition, according to Bayes' rule, you can construct it by taking the probability of measuring E given rho E T2, T1, E1 times the probability of measuring E1 given rho E T1. Okay, which once you do the math, turns into PE rho E T2 0 E divided by PE rho E T1 E1. So this is this probability of get conditional probability for E2 times PE rho E T1 0 E1. So this is this. Of course, they simplify and you get P rho E T2 0 E2. So I think that the emerging pattern should be clear by now. All right. So the probability of measuring E1 at time T1 is a diagonal part of by probability. Probability of measuring sequence E2 E1 is also a diagonal part of probability. So you can imagine that if you want to do n steps, probability of measuring this whole sequence given the initial state we will find that it's equal to the diagonal part of by probability associated with observable that we are measuring. So this is another context when by probabilities comes up. It's not only multi-time correlations, not only open systems, not only dynamical maps and stuff like that. It also comes up when you are considering measurements, sequential measurements in general of observables in a system. Okay. So far we haven't. So far I haven't said anything about validity of surrogate field representation. So this is a general result. Okay. So it is true that probability of measuring a sequence is given by a diagonal part of corresponding by probability distribution. Okay. So this is a general result. But now let us indeed assume that we have a valid surrogate field representation. So if we have a valid surrogate field representation, then these probabilities they become consistent, right? They become consistent. So in other words, those probabilities here are the same as a probability for sampling a trajectory of a stochastic process E. If surrogate field rep is valid, PE rho E Tn En become consistent. Become consistent, right? And therefore, our measurement, our observation that we are doing is then equivalent to sampling is consistent. Therefore, a sequential measurement is equivalent to sampling a trajectory, unitrajectory of stochastic process ET. Right? So in other words, if TET is a sample trajectory, of process E, right? Then E1 equals E at time T1. The thing we measured is as if we probe the trajectory, and this is the value we found out. You know, E2 equals E at T2, and so on until En equals E Tn. All right. So the fact that the probability of observing a given sequence is the same as the probability of sampling specific values for a trajectory of process E, right? It means that our observations, the observations of the classical observer, are also like observations of a quantum observer, right? We are experiencing this observable E when the surrogate field representation is valid. We are experiencing this observable E as if it was a trajectory of a stochastic process T, okay? So this is the same, it is the same kind of experience as this uh, as the quantum observers have of the process. And it is really, our classical observer perception of those trajectories is really the same as the perception of uh, quantum observers, because you can, uh, you know, if you are able to do these sequential measurements of E in the surrogate field representation, uh, then you can store your results. Okay, you can store your measured sequences, and then you can take those sequences and treat them as an ensemble of sample trajectories of the process E, which then you can use to approximate the stochastic averages of the stochastic averages you can encounter when calculating some stuff for dynamical maps or anything else, right? Because you can do this. This is you can use those samples as those measured sequences as samples, because the probability distributions for your measurements, as well as probability distributions that govern this stochastic average here, are the same. These are the same probability distributions, right? So for all intents and purposes that you can imagine, whatever you imagine you want to do, those things, the things we measure as classical observers, are actually the same trajectories that are driving the quantum system as coupled to this observable. So it is indeed the intersubjectivity extends beyond quantum observers. It also encompasses the classical observers as well. And if this is the case, you have quantum observers, you have classical observers. Is there any other category of observer that we can imagine? I think not. So we have an intersubjectivity among all kinds of observers, at least all kinds of observers I can imagine. So this is a categorical upgrade for this intersubjectivity. So I think this is what allows us to say that when the surrogate field representation is valid for a given observable of a system E, then this surrogate field becomes an objective entity. Objective because all possible observers will experience this observable in the same way, in the same fashion. They experience it as this stochastic process with unit trajectories, right? And whether this is the case, it only depends on the dynamical properties of the system the observable belongs to. So this is, on the one hand, this gives us the explanation for the origin of external fields in quantum mechanics, right? So this is the mechanism behind behind those effective Hamiltonians when you have some system operators coupled to some external field, maybe noisy field even. But it also, because of this objectivity, it also gives us a recipe for a classical limit for quantum mechanics, because if you have this observable that behaves as a stochastic process, as this external field for all observers in all possible contexts, then this is what a classical limit should be, because this given observable, it behaves as if it was governed by a classical theory rather than full quantum theory. Not because the dynamical properties of the system the observable belongs to are such that the bitrajectory stops being bitrajectory and it collapses into unitrajectory, just like any other classical system, any other classical observable. And I think that should be it for this topic. I hope you found it interesting. I think I turned it into technical nightmare again. I'm sorry for that. I couldn't. I think I couldn't avoid that. But I think this was like this closing philosophical deliberation. I hope it was change of pace, and I hope it was also interesting for you. And this also ends the course itself. So yeah, I hope you liked it. I hope it was informative for you. You know, if the my explanations weren't clear enough, you can, hopefully you can always fall back to the my written paper, written notes, where all those things I tried to say here in words were written with maybe a little bit more grace, a little more clarity. So whenever you want to refresh the material went over, please check out the notes. I will be updating them over time still because I want to release the second edition of the notes uh, based on based on the adjustment I made along this edition of the course, of those lectures I gave it. Uh, yeah, so I think that's it. So see you, hopefully see you in the next course.